Synthesizing complex macromolecules, specifically the insertion of metals into porphyrins for sensor applications, presents a severe optimization problem. The chemistry requires extreme precision to avoid side reactions. The primary barrier to scaling these synthesis reactions is not a lack of theory, it is the sheer volume of experimental parameters that must be tested to find the exact optimal physical environment. To run a single metal insertion, chemists have to juggle multiple options: distinct metal salts, varying mole ratios of the reactants, different organic solvents, and a range of reaction durations. Factoring 6 salts, 3 ratios, 5 solvents, and 4 durations results in a combinatorial explosion. Facing over 1,000 permutations through trial and error exacts a massive toll, consuming rare catalysts, generating unwanted side reactions, and wasting days on dead-end pathways. Relying on physical guessing to find the right conditions is economically and practically unscalable. Modern chemistry requires a systemic shift, mapping the parameter space mathematically before committing to physical experiments. To bypass this bottleneck, researchers constructed a mathematical filter to evaluate the chemical parameter space before a single beaker is touched. They deployed a multi-criteria decision-making framework known as the Analytic Hierarchy Process, or AHP. AHP is typically used across heavy industries, from power grid modernizations to pharmaceutical supply chains, to structure complex, multi-layered decisions. Instead of relying on intuition, chemists input qualitative literature heuristics, data on cost, material availability, and known kinetic behaviors. The matrix then converts those variables into rigid, quantitative rankings. The objective of this study was applying AHP to isolate the single highest yield condition for palladium and platinum insertion out of 1,080 possible combinations. By utilizing this process, the heavy lifting of optimization shifts away from expensive manual bench trials and directly onto an efficient computational algorithm. The first phase of the AHP methodology requires organizing the chaotic variables of the chemical reaction into a strict analytical hierarchy. This model starts with a single objective positioned at the apex, identifying the exact conditions for the highest reaction yield. That overarching goal is broken down into the 4 primary physical criteria that govern the reaction: metal salt, mole ratio, solvent, and duration. Finally, the model expands to its foundational layer, dropping a web of specific chemical alternatives directly beneath their parent criteria, mapping out all available salts, solvents, ratios, and times. This top-down visual hierarchy is an essential prerequisite. It explicitly defines the absolute boundaries of the chemical experiment before the mathematics even begin. With the structure set, the model utilizes its mathematical engine, SADI's 1-to-9 scale. Rather than evaluating every variable simultaneously, the matrix forces a pairwise comparison. The criteria are pitted head-to-head to establish explicit priority. These numerical comparison scores are driven by empirical data. They reflect decades of historical chemical literature detailing which factors bottleneck the metallation of porphyrins. This chart shows the final AHP weights for the primary criteria. It reveals a dead tie for the most influential factors in the synthesis. Both the choice of metal salt and the reactant mole ratio carry an exact 33.1% weight. The physical ingredients strictly dictate the probability of the reaction's success. The remaining physical conditions, the solvent at 23.7% and duration at 10.1%, are important, but mathematically subordinate to the raw chemical inputs. The matrix proves a harsh kinetic reality. Perfectly optimized environmental conditions cannot rescue a poorly chosen combination of physical reactants. The model then drills down from the broad criteria to evaluate the specific chemical alternatives at the bottom of the hierarchy. This chart compares the 3 mole ratios tested. A ratio of 1-to-3 vastly outperforms the alternatives, locking in a dominant 81.8% performance rating. The chemical logic here is precise. Minimizing the ratio to 1-to-3 hits the exact threshold needed to maximize metalloporphyrin synthesis while halting the costly waste of excess metal ions. This chart evaluates the 6 metal salt options. Palladium acetylacetonate, or PDACAC2, takes a commanding lead at 43.7%, leaving palladium chloride and the platinum variants trailing far behind. The algorithm's kinetic evaluation confirms that palladium-based salts dramatically outperform their platinum counterparts, which are heavily hindered by slower complex formation rates. Finally, this chart compares the 5 organic solvents. N-methyl-2-paralidenone, or NMP, rises to the top at 40.4%, cleanly beating out benzonitrile and acetic acid. NMP ranks superior in this model due to its high polarity and an excellent dielectric constant, making it exceptionally well suited for rapid energy absorption. Out of 1,080 blind permutations, the AHP algorithm successfully isolated one mathematically defended, highly specific chemical recipe ready for physical testing. With a specific theoretical recipe isolated, the narrative moves from the algorithmic model back to the physical laboratory bench for empirical validation. Researchers first established a baseline using the classical heuristic-driven method for palladium insertion, which relies on palladium chloride salt submerged in boiling benzonitrile solvent. This classical approach requires a grueling 24-hour reflux heating period just to achieve a 68% reaction yield. When researchers attempted to speed up this exact setup by placing it into a modern microwave heating unit, the elemental metal formed severe electrical arcing, resulting in a 0% yield. Legacy chemical parameters cannot simply be brute-forced into modern acceleration technologies. To achieve efficiency, the entire parameter space must be updated synergistically. The chemists then deployed the specific parameters output by the AHP decision model to test against the classical baseline. They ran the precise algorithmically chosen combination, PdACAC2 salt, a 1:3 mole ratio, and the NMP solvent. The laboratory outcome validated the math. The optimized reaction produced a high purity yield of 81%. Most critically, the synergy of the NMP solvent and microwave heating allowed this 81% yield to be achieved in exactly 15 minutes, drawing a sharp contrast to the 24 hours required by the classical method. There was one specific anomaly between the model's theoretical prediction and physical reality. The AHP model originally assigned the highest performance rating to a 24-hour duration based on historical literature. The empirical reality proved different. The AHP-selected NMP solvent matched perfectly with microwave heating, shattering the conservative timeline estimate. This creates a closed feedback loop. The newly discovered 15-minute kinetic reality is fed directly back into the matrix, automatically adjusting the algorithmic duration weight for future predictive models. The AHP decision model does not replace empirical chemistry. It serves as a precision targeting system, systematically eliminating waste and converting 24 hours of exhausting trial and error into 15 minutes of maximized scientific output.